Part 2. Okay. Welcome back. So that will be the 5th session of the series of lecture in Nonstationary Time Series Analysis with modern signal processing techniques. So remember, what is the ultimate goal? The ultimate goal is to find ideal time frequency representation as we just defined. This is the ideal time frequency representation. Suppose we can achieve it, then we can easily achieve the component decomposition, recover instantaneous frequency, get all the dynamics and so on. That is our ultimate goal. But as we have seen in short-time Fourier transform, it doesn't seem to be the case. Short-time Fourier transform actually, with other linear type and or even quadratic type time frequency analysis tools, they are limited. I do not say they are useless. They can be very useful, but you need to know how to use it. But for our ultimate goal to get ideal time frequency representation, they are limited. And this limitation can jeopardize several signal processing purposes, which we will discuss in a bit. So we need some, maybe more ideas. And what can we get? What can we do? So one solution I will introduce here is called synchrosqueezing transform. And there will be some other transforms, some other algorithms we will discuss on the road. Okay? So that you have an idea of what we can do, what algorithms are available nowadays, and how to choose the proper one when you do signal processing. And this is a list of reference of synchrosqueezing transform, and there have been several. If you need any of them, maybe you can take a look. And there is a more general setup or reassignment in general called reassignment, which actually was first proposed back in 1976. Very, very old idea, but turns out to be revived in 1955, and then followed by synchrosqueezing for reconstruction and several signal processing purposes. And there's a review article published, remember, 2-3 years ago, which I try to contain some information, but that is a bit of maybe not that out of dated, but well, there are some new developments in the past 2 years. So yeah, but we'll go there. And the idea I will tell you about synchrosqueezing can be also generalized to several other transforms, which we may or may not be able to detail, but there are several publications that you can check. And this is the MATLAB code. If you are interested in getting the MATLAB code, the implementation of synchrosqueezing and all the other algorithms for your data, you can scan this QR code and download the MATLAB code. In case you need it doesn't work, you can send me an email. I will share the code with you. Okay, so let's go into the algorithm synchrosqueezing transform. I will use this very, very simple, very ideal signal as an example. So in this signal, you see the amplitude is fixed 1, but frequency increases. That's very nice, and probably the best signal you can imagine. If you can get it, wow, life is easy. We will use this signal as an example. First, recall what spectrogram is. You run spectrogram and you plot the frequency representation. Okay, and you may pay attention, which we will come into detail later in the series of lectures. That is near the boundary. Near the boundary, you see something a bit weird. This is the boundary effect. Because near the boundary, the window can only see half of the signal. So you get some asymmetry. So the window behavior changes near the boundary. That is a very common boundary effect. We'll discuss how to fix it later. If you think about it, look, short-time Fourier transform is a Fourier transform, right? So if the signal itself is real, if the window is real, then after Fourier transform, the signal, the shorthand Fourier transform, should be a complex valued function. But when we discuss spectrogram, what do? We took the absolute value to evaluate the magnitude of the shorthand Fourier transform and represent it. We did not pay attention to the potential phase information hidden in the shorthand Fourier transform. So, can we leverage the information in the phase? Answer is yes, yes, yes. This is the phase. And how do I evaluate it? I just simply evaluate the phase of the shorthand Fourier transform. Maybe it's better I write it down. Okay, where phi t c is in 0 to pi. Okay, and what you do is, if you take this absolute value function, you take square root, that is a spectral, right? And this is the so-called phase. And what I showed you here is the phase. There's a phase, how it looks like from 0 to pi, from minus pi to pi actually. This is the plot is minus pi to pi. So you see, this is kind of very beautiful wave-like behavior, isn't it? And what you can see is, if you pay attention, in the low frequency region, the wave is wider. But in the high frequency region here, the wave is shorter. Right? So the wave encodes useful information about the oscillation. Can we leverage it? And you can see there are some interesting pattern here, right? Pattern here, when those are coming from the boundary effect I mentioned. So what we can do is, how about if we take a closer look? We just multiply the spectrogram and the phase, and that is what you get. So over this region where the spectrogram is strong, you can see a very nice oscillatory pattern, isn't it? Which seems to follow the frequency. And if you pay attention to compare these two guys, you see here, away from the oscillatory region, there is some kind of deformation of the phase, but that's not our concern today. Everything over here seems to give you reasonable information. So how to use it? The overall idea is the following. We want to take the phase information and try to modify the shorthand Fourier transform or modify the spectrogram in this way. We take the phase information and we modify the shorthand Fourier transform by something we call squeezing. And we'll talk about squeezing in a bit. To achieve this goal, we first evaluate something called reassignment rule. And this reassignment rule looks a bit weird in the very beginning. That is, you evaluate minus I divided by 2 pi, and you have partial t, you take a temporal derivative of the shorthand Fourier transform divided by shorthand Fourier transform. And this guy, formally, okay, can be written if you choose the branch properly and the phase properly. You can evaluate, you can view this as the partial t of log. Right? This is partial t over itself. So this is log partial t. You need to be careful because there'll be some singularities appears. And this is defined when the shorthand Fourier transform is not 0. And we just put 0, sorry, this should be minus infinity or something. Minus infinity. 0 would be weird because we sometimes need to change. So this is minus infinity. Sorry, this is minus infinity. when VF is 0. And this is called the reassignment rule. Okay, before I tell you what it is, this complicated, weird formula is, I want to mention that the similar idea holds for other types of linear, the other linear type time frequency representation, like short time Fourier continuous wave transform or S transform and so on. Similar idea. Now, to appreciate what this reassignment rule is, let's take a look at this very simple example again. This ft is a cosine C0t, harmonic function, nothing crazy, nothing special. And now let's assume the support of the window in the frequency domain is over minus epsilon epsilon. To avoid complication, we also assume that epsilon is smaller than C0, the frequency. That's a very simple assumption, but well, if it is not satisfied, then we will have to control the arrow turn. But arrow turn is usually easy to control, but it will just looks more tedious. So that if you just consider the initial partial t of VF, that is what you get directly from this guy. Everything's analytic, everything can be done. Easy. Now you evaluate omega f, the reassignment rule. Then what do you get? You will see that when eta is inside C0 minus epsilon and C0 plus epsilon, V in general is not 0. Oh, sure, we have to assume that H hat is not 0 inside this region. Then you get C0. But if eta is outside this region, we just get minus infinity. So what do you get? Very easy, you get the frequency information. But this is harmonic function, come on, this is so easy. There's nothing really we need to do, right? But this serves as the preliminary model. If you are working with adaptive harmonic model, as you can imagine, all these can be derived in a similar way by using Taylor expansion. And so that you can approximate instantaneous frequency with some small error, controllable error, okay, in general. And this is a basic idea. Very informal argument without going into calculation is, you see this guy is this log partial t, and if we write short time Fourier transform as amplitude and phase, and then we take the natural log and partial t, what do you get? The natural log of this guy is not log of absolute value plus partial t of the phase. Very simple. And now remember what we assume. We assume that the amplitude of the signal does not change too fast. It changes slowly, locally. So the short time Fourier transform magnitude will also change slowly. So after taking log, it's like constant. Taking partial t, it's like 0. So gone. What you get will be the phase derivative. And the phase encodes instantaneous frequency. So that's an informal argument, but this is how it works. If you want to do calculation to really prove it, it's just tedious. And you need to carefully control different terms. So now let's take a closer look at this reassignment rule. You now recall this is the phase of VF. But what about the phase of the partial derivative? There's a very interesting transition, segmentation here. You see, the phase are different. Very interesting part. And then you evaluate reassignment. That's what you get. Some part you need to shift, some part you need to shift down. That is how the reassignment rule looks like. And then finally, we can apply this reassignment rule to achieve our final algorithm called synchrosqueezing transform. What we do is we simply take the short time Fourier transform, okay, and we evaluate the reassignment rule, and we say that, hey, if we want to detect at time t, if there is anything that oscillates at frequency c, then what we do is we go through all frequencies eta and check if there is any if this component, if in short time Fourier transform at frequency eta, if it oscillates like frequency casino, if it oscillates like it, which is measured by this delta major, okay, then we sum everything. We sum it together. That is, in other words, we try to reallocate all the short time Fourier transform coefficient to frequency eta if those eta oscillates at frequency casino. But here, certainly we need to be careful about this delta, how to use this delta, because it's a delta major, and this is a nonlinear function. So usually, when we seriously write this down, we need to use approximation, like Dirac approximation, and so on, Gaussian Dirac approximation. But this is some technical details I will ignore. Then this is how you get. This is the result. After you run this squeezing, you just get a very beautiful curve. And there is a boundary effect, as I told you, boundary effect. So that's the synchro squeezing. In this super simple example, which you actually don't need synchro squeezing, you can achieve anything you like using short time Fourier transform. And let's take a look at a real world signal. So this is a respiratory signal you saw before. It is its spectrogram, and it is it's a phase multiplied by the spectrogram. Okay, and as I told you, we can use the phase information to do reassignment. And the reassignment comes from the phase information, and you get this very beautiful curve. And this curve reflects what? It tells you that, hey, the frequency slow, so the frequency is 0.2 slow. But frequency here, it oscillates faster, so the frequency is faster, 0.25 somehow. And the intensity is weak here, small here, and weak here, which this should be updated. This plot is not, this is maybe too weak. And this is another look at synchro squeezing transform. This time I put everything together. This is a PPG signal, photoplexismography signal. This is the phase. This is the multiplication. Okay, and this is a synchro squeezing transform. This is a spectrogram, and this is a resulting synchro squeezing transform. And if you pay attention to compare short time Fourier transform and the spectral and synchro squeezing transform, what do you see? You see a very clear difference. That is, first, it is kind of sprayed out. It is sprayed out, right? But this is very, very sharp. And here, also you can say, hey, we can also see instantaneous frequency information, but there is a lot of garbage in between. A lot of garbage in between, which comes from trend, low frequency, and so on. But this is kind of suppressed. So you can see a much better contrast in between the signal and the background. And also, if you pay attention, this is 1, 2, 3, 4. It is less easy to visualize the force component, but here it is still visible. Visible doesn't mean good. Visibility doesn't mean good. It only helps us to do some justification. In the very end, you can always change the scale of the representation. For example, you take square root, you take square, you even take log of the time frequency representation to see different details of the time frequency representation. There are many different ways. Okay, but in this picture, no matter what you see, what you say, the contrast is the key. This contrast will be preserved under monotonically increasing or decreasing nonlinear functions, so that you can catch, at least visualize the critical information we are interested in. Okay, this is another view to help you to understand how the synchro squeezing work, the squeezing part. Again, this is a window, and you truncate this part, and you evaluate short time Fourier transform, you see some spray. Okay, I forgot to mention that this windowed idea Fourier transform in time frequency analysis is called tapering. Oh, so we are doing tapering. Okay, So you can see some spreading, and you evaluate the reassignment rule. And the reassignment rule, at one time, it looks like this. You can see over this region is very flat, over this region is very flat, but all the other region can be random, but we don't care. Okay, then what you do is over this region, here, okay, this reassignment tells us, oh, you should go to 2. Okay, so we just move everything to 2. Well, sorry, not 2, 1.5, 1.6. Okay, and over this region, the reassignment rule tells us, hey, you have to move to maybe 3.1. Okay, so we move to 3.1 or 3. That is how the synchrosqueezing works. It's a very nonlinear operator, and it gives us some useful information. Not everything, but useful information. So again, let's take a look at some simple calculation. Okay. So we have the function a, again harmonic function, and we take some g function which is compactly supported to approximate the delta measure, as I mentioned before. So you can rewrite VF, right? And you know VF is supported at c0 plus c0 minus epsilon to c0 plus epsilon. And you evaluate this guy, and you put everything back. Okay, then you can evaluate. In the end, what you get, G is out, Fourier transform. Okay, so you get some kind of reconstruction of the signal. Synchrosqueezing will give you, sorry, not reconstruction. Synchrosqueezing will give you the information centered at C0 when alpha is very small, and over this region, you get also the phase and amplitude in front. And that is when C is inside C0 plus alpha times support of G. Sorry, support of G, yes. And 0 otherwise. So in this sense, synchrosqueezing helps you when alpha is very small to get the ideal time frequency representation. In this sense, which we will see in a bit. And this is this is how the signal looks like in the continuous setup. But in numerics, what the implementation is actually very simple. You simply do direct discretization. As you can imagine, this is a kernel method. Everything is kernel. And the kernel methods, the best way is just to do uniform discretization. Maybe there are better ways, but I'm not a numerical analyst. So for better tricks, I will count on them. But what we do is just do some very simple Riemannian sum and the synchrosqueezing as well. In the frequency domain, also do some direct discretization, and you can implement it. The code, the MATLAB code I shared with you, is essentially implemented following this idea. So the overall implementation actually is linear time complexity, because at each time you only take a small window. So the complexity is this size of window times log of it. Like if the size of the local window is m, it's m log m. But if you have n points, it is n times m times log m. So you can do some online analysis if you need it, but you need to handle the boundary effect, which we will cover in the end. Causality is almost preserved. Okay, real-time implementation about this online analysis, we'll talk about it later, and how to eliminate the boundary effect. So far, we have somehow achieved the visualization purpose, and we will do change detection later and decomposition later, very quickly. So let's take a look at another challenge. Immediate challenge is the following. What about if the signal does not satisfy very well or cannot be well captured by adaptive harmonic model? That is, the frequency may change very fast. The frequency may change very fast. Then what will happen? So in this signal, you can see it oscillates here and suddenly become very slow and it go back to fast. Its short-time Fourier transform looks like this. And its phase becomes super beautiful. A lot of branchings and so on. How to study it? That's something needs to be further explored. It's very beautiful. But no matter what, over the short-time Fourier transform region, like when the short time Fourier transform is large, you can see, well, this is kind of curved, right? But over this region, that signal changes very fast. You can see there's a beautiful crescendo curve. What is it? Then in the synchrosqueezing transform, you can see a big spread. A big spread. Okay, so it doesn't really give you very sharp time frequency representation. So the idea, can we further improve it? Yes, we can do it. Then what we consider is the group delay or temporal information. That is, we consider another window called x times h, th, and you do the evaluation like before. But this part I will skip all details, but you can see it can be evaluated in different ways. And this guy is actually group delay of the short time Fourier transform. And then you just consider not only the frequency domain reassignment, but also temporal domain reassignment. Okay, you consider extra reassignment. And because you consider different time and frequency, so you have double integration. And in the original proposal, the reassignment rule back in 1995, you take square, like the spectrogram to do reassignment. But then if you do so, then you lose the causality and cannot do the reconstruction. So what we can do is we can consider a variation called soft real-time reassignment. That is, you consider VF, not the spectrogram, and you only consider some Q parameter that you want to control the soft real-time and do the reassignment. Okay, and this is the result. You can see that this spreading part is somehow corrected. Although you generate some interesting small patterns. Okay, interesting small patterns. Okay, and this is another figure from my collaborator's paper. They have this beautiful chirp, and they have some kind of oblique reassignment, vertical reassignment somehow, and this vertical reassignment allows us to do reconstruction. But both allows us to achieve instantaneous frequency reconstruction. So in the end, we get a sharper, not causal, but future information is needed if we consider the reassignment. And you can also, then you can see that we actually use the phase information from different aspects. And if you modify the algorithm slightly, just very slightly like before, then you can achieve this second order synchrosqueezing, and this is the result. It becomes much sharper, much sharper. And in the code I shared with you, all these are kind of implemented. You can just try and see how it works. Usually, in practice, second order seems to be more balanced. Higher order is useful, but seems to be you have more troubles when the signal is noisy. So usually, when I apply synchrosqueezing, I consider second order first, or first order when the signal doesn't have fast instantaneous frequency changes. Okay, that is about synchrosqueezing algorithm, and this is for this session. 30 minutes, right? Good.